Welcome to qnawire.
Now this question we have this particular circuit with a battery, a diode and a resistor. We're given various properties of this resistance or the diode itself, but what we want to show is using Kirchhoff's loop rule to find an equation. So let's start off by the Kirchhoff's loop rule. We know that we want to follow the direction of the current. We're going to follow this loop over here, which is in the anti-clockwise manner. So starting from the battery, we are moving from the minus end to the positive end. So we'll add the EMF. And then we have this potential drop across the diode, right? Delta V. So we will subtract that because we are moving in the same direction as the diode. And then we move past the resistor in the same direction as the current that is passing through the resistor, so we will minus also the potential drop. So the potential drop over here equals to I times R, current multiplied by the resistance. And by Kirchhoff's loop rule, this must add up to 0. So rearranging this equation a bit, we get epsilon minus delta V is equals to I times R. But what is I? So I is the same as the current in the diode over here, and we can replace this I with just I naught e to the power of E delta V over kBt minus 1. So this is the current passing through a diode equation multiplied by R. Because they share the same current, so they must have the same description, right, which is the current passing through the diode. Now we want to solve for this by plotting actually two graphs, and we want to find the intercept between these two graphs. So what are the two graphs they're going to draw? Well, for this you'll need a graphing calculator, but for me I'll just sketch it out for you, what the graphs will most likely look like. You want to graph with respect to delta V, right? Which is because we want to find what is our delta V. So I'm going to plot a graph y equals to epsilon minus delta V, and we also want to plot another one, y equals to I naught R times E exponential E delta V over kBt minus 1. So these two graphs, one is an exponentially increasing graph, and the other is just a straight line, right? Y equals to C minus X, something like that. So for this graph, over here, the x-axis will be our delta V, alright, and then for the first equation, y equals to epsilon minus delta V, when delta V is 0, this will be your epsilon. It's about 2.42 volts, and then it's a negatively downward sloping curve with gradient of minus 1. So something like this, not very accurate. You should use a graphing calculator. Kind of like a downward sloping curve. On the other hand, for the y equals to exponential term, right, so we have I naught R exponential when delta V is 0, this entire expression, the exponential term will be 1, so 1 minus 1 is 0. So it actually starts from 0 over here, and it goes up exponentially, something like that. So you should plot this in your graphing calculator. And using the graphing calculator, you should be able to identify what is this intersection point. This is the intersection point when these two curves agree. That is when E minus delta V is equals to I naught R times this exponential. Right, and this is how we solve for this equation numerically for delta V. Right, we just take this delta V, and with the calculator, we should identify this delta V to be about 0.2 volts. Now to find what is the actual current in our circuit. Right, we're going to find the current in the circuit. We substitute in this value of delta V into the equation for I. So I is just I naught I naught is given to be 10 to the power minus 6, right, 1 microamps, so just 10 to the power minus 6 amperes. Delta V is about 200, sorry, 0.2 divided by kBT, Boltzmann's constant, and the temperature. So the kBT is given together to be 25 milli electron volts. So this is 25 times 10 to the power minus 3 eV. So what we're going to do is we're going to keep this as E, right? The charge over here kept as VE, so that multiplied by this 0.2 volts, we get 0.2 eV. So we just take 0.2 divided by 25 times 10 to the power minus 3. Right. Minus 1, of course. And the entire expression should evaluate to 2.98 times 10 to the power minus 3 amperes. It's given as 2.98 milliamps. Now using this, we can find the resistance of the diode. It's just V over I, where V is delta V, and the current is 2.98 times 10 to the power minus 3. Delta V is 0.2 volts. Should get 67.1 amperes. Sorry, not amperes, 67.1 ohms. Now on the other hand, to find the dynamic resistance, now the dynamic resistance is given as D of delta, differentiating delta V with respect to the current. This is actually can be written as inverse of di d delta V. So we can actually differentiate the current equation with respect to delta V and then we inverse that expression. So we differentiate this with respect to delta V. Right, so from here, again, we just substitute in the various values in, and then we inverse the entire expression. So we already have all the values, right? Delta V is just 0.2 volts. KBT is given as 0.025 EV. And then the I naught over here, 2.98 milliamps. So we should get overall about 8.39 ohms. I just take note of the units, especially for the terms outside the exponential term, because this is 2.9 milliamps. We will convert it into amps. Multiplied by this E divided by 0.025 EV.